But I'm getting 4 or 5. But I don't know. But I don't know. It's like after time, it's like okay, what is like when you see that you talk about the eye, it's yeah, like like oh yeah, so this is a good probability because it's not like you see it in let me guess 182, 251, 381, 416, 350. There are a company times.
Okay, I guess we can start. Sweet. Pizza was supposed to be here, but it's not. And I'm sorry about that, but we will figure that out. Hopefully, like it comes at some point. Anyways, so today we're going to be talking about, I guess, part two of AGOP as a mechanism for deep neural collapse. This is probably one of the favorite set of papers that I've had a chance to read because it combines a couple of things I like the most: ML theory, interpretability, and some aspects of optimization. It's actually, wait, before we get into what it is, how many folks were here last 2 weeks ago when we covered the part one? Right, we got one. Sweet. Okay. So I probably will have to get into the detail, but it took an hour for us when we got into the detail of DNC. So I don't want to read on. We'll try to keep this a bit high level at the start and then go deep for what AGOP is. But the overall idea between the entire title is that we are going to discuss a mechanism called deep neural collapse, which is a phenomenon that is observed when we overtrain neural networks. And that phenomenon is something that is very useful for generalization. And it is actually the optimal setup for generalization. And average-graded outer product is an interpretability technique that uncovers how neural networks learn features, and that itself induces the property of deep neural collapse. So we are basically learning a lot about why these neural networks are able to work so well, because we're decomposing them into parts that are actually carrying out the learning, so to speak. So to recap what deep neural collapse is, or the overall architecture of what we're going to cover is just, we first talk about deep neural collapse, then AGOP, which is the interpretability technique, and how AGOP, the mechanism, induces deep neural collapse. So background and intuition, we discussed the fact that support vector machines are a very useful analogy for how deep neural networks learn, in the sense that when we have data that is not separable linearly, we use kernels, which is basically taking our inputs, which is in R2 dimension, to a higher dimensional feature space, and using that in order to basically learn a hyperplane. So instead of learning and identifying this plane that is able to separate the blue and the green dots, we are learning a plane in high dimensions. And when we compress that high dimensional structure back into 2D, we get a nonlinear decision boundary. And to a certain extent, deep neural networks are doing much of the same thing, wherein if we take an example of ACNN, so we will talk about classifiers for the entirety of this presentation, and DNC is deep neural collapse is a property that is restricted to the classification setting, not the regression setting. But the deep neural collapse as a phenomenon within the paradigm of the classification setting doesn't really care about the domain of the problem. So image tasks and NLP tasks and any sort of task, basically the properties that hold. So we can discuss it with respect to images because it's easy to talk about, but we are not using any generality when we discuss that. The idea that I was saying, or the connection with respect to the support vector machines that I was presenting, was that the entire part that is learning the features, right, is sort of oh, right, here. Yeah. We can probably take part to come grab pizza and get it.
And then we explain that to me, it's better than 35.
Thank you. Have you nice. You do. Thanks.
Oh, yeah, go for it. Yeah, please.
You know, I'm going to be talking about SVD soon.
Oh, no. What did you say?
AGOP uses SVD very well. I mean, it's actually cool. You don't feel bad at it.
This time you certain topics, you stage of like last semester, you told me 10P and to compete really optimal. I would like want to go.
I agree. No, but like you feel upset.
Anyway,
Like you will love SVD after.
I love SVD. It's helpful. Just that I don't want to do it. Fucking do that. Make it by hand.
No, can do it back.
That's what I'm saying.
That is.
I would have fucking written the numpy code to do it.
That's not what I was thinking about it.
Yeah. I have to do it by hand.
Oh, by hand?
That's why it's useful. It's like I know all the content. I know what you're talking about. I just don't want to do it. If you tell me like, yeah, like it's a whole bunch of yeah, I look and I say, oh, I can do PCA. I use PCA. You're like, oh, we actually do PCA by 100 by 100. Yeah, this is my favorite. Huh?
I got it.
Yeah.
Oh, okay. You nothing.
I know.
Go for it.
I mean, if provided that everyone has gotten the slides, does anyone want more pizza? We have, I think, almost a whole pile.
It's gonna be my plate.
Okay. All right, sweet. I'll give us an extra second and we can continue. Okay, so, deep neural networks, deep class. Yeah, okay. We were talking about image classifiers. We have the convolutional backbone, which is what is doing much of the feature learning. And then the final classification is done usually by a smaller set of fully connected layers. The idea is that the backbone contains information that is relevant to or like it constrains our search to the neighbors of all of these of the specific kernel. So you basically go across the image with over the kernel and only constrain neighboring pixels. So this pixels evaluation does not really see this pixels evaluation. And that is something that is important because we are sort of preserving the fact that pixels closer to one another have some sort of inductive meaning and being invaded to that position of the image or the structure of the image is generally a bad idea. The main or like the main interesting thing that we observe when we sort of get past the point of optimal accuracy is optimal accuracy is called overtraining the model, and that is what basically leads to the state of deep neural collapse. So I don't think my drawings from before I'll just redraw it. Okay, so to demonstrate what overtraining is, right, is basically when you train a model past the terminal point of training called the TPT, And the terminal point of training is basically when we compare our training accuracy and our training loss. So if I just draw these two plots, uh, so as I start training my model, it will probably have poor accuracy, but as I sort of train it for a particular period of time, assuming I have an expressive enough model, I am going to get to a point where the accuracy is basically like 100%, right? And this is basically an optimal model in the sense that every single prediction that it gets is able to classify it correctly within my training set. So I should probably mention training, and we are also training. And loss is much of the similar thing where it is reducing, but at the time of the training accuracy reaching 100%, if we extend this down, we see that this is not yet zero, or this is not yet optimal. So if the optimal loss is 5, it is not yet 5. And if we continue to train our model beyond this point, it seems like there is really nothing to gain, right? I have reached 100% accuracy, but I have not yet really reached the ultimate perfect loss, and it might take forever to reach that because it's reducing very, very slowly. But yes.
How do you know what is the optimal loss?
I think that is known, right? Like it's not optimal loss with respect to a particular model architecture, it's just optimal loss in general. So if I'm saying, if I'm using cross entropy loss, right? That's just the negative log likelihood. The minimum negative log likelihood is going to be 0. So if I'm doing mean squared error, again, the minimum error is 0.
Right, but like you just said, like you just threw out the number 5.
Yeah.
So how do you know it's not number 4 or 3?
That depends on the formulation of the loss function, right? So if you
it just depends on like mathematical.
Yeah, the mathematical optimal. Suppose you have the oracles that can predict every single
I just thought it was
thing.
empirical, that's why.
Oh no. It's predefined basically. As someone who designs the loss function, you know what is the minimum that you can possibly get on it with the best performing model. And basically, once you continue to train your model, so this is not 0. And you continue training your model, you see something very interesting in the final layers of the architecture that we're basically investigating. And this is sort of described in this diagram over here, where there are actually 4 different characteristics that we are trying to look at. Also, what time is it? 8:15. Okay. There are 4 different characteristics that we are looking at, and they basically quantify what a deep neural collapse is. So if all of these 4 features or all of these 4 characteristics are met, we have achieved the state of deep neural collapse. And this is very important or very useful because deep neural collapse has actually been proven to show optimality of risk. So if this structure that I'm going to talk about in a second is met, you are going to basically get your maximum performance through there, your maximum generalization through there. So this structure, the structure on the very, very right, is actually the risk minimizer for population risk over your entire data distribution and not just the data set that you are training on. So this is something that is very cool. To talk a little bit more about the diagram, right? We have basically the final layer visualized. So the if we have, let's say, k classes and I data points within each class, so n data points within each class. So we have a total of k times n data points. We have a penultimate feature vector that is demonstrated by fki, and that penultimate feature vector is basically what is plotted, and the class means for those feature vectors are plotted in this final frame. So the penultimate feature space is in 3 dimensional, is in 3 dimensions, and there are 3 different classes. So there are 3 different spokes, and we are able to see it in like a visualization of 3D, which is why we know it's an R3. So the idea is that we are basically looking at this through training. So maybe the first one on the left is like at the start of training. And this is maybe once we have achieved 95% accuracy, this is what we get 100% accuracy, and this is what happens after we completely overtrain it. So the interesting observation that we can make is that the points are basically reducing in variability. So if I have a data point X, maybe it is plotted as this thing over here, and then slowly it gets like over the next phase of training, it goes all the way to here, which is the class B. And this is something that is very interesting because it's basically sort of quantifying what the specific image is to a specific class by assigning a certain mean to that class. So this is the penultimate layer. It is not the final classification. The final classification is from R3 all the way to R1. And if we go back to our analogy of the SVM, the kernel of the SVM is trying to just make the features linearly separable. Then you can take a hyperplane, slice through the data, and then call it a day, because a single linear classifier is able to basically solve your problem once you apply the kernel, right? So that is similar to what we're doing over here, where the entire backbone is being the kernel, and then you have a final layer that is just performing a linear classification. Question?
Yeah, I have two. So the first one is like, can you please explain again why it's like counting layer completely?
It is because the output of the backbone is in R of 3.
Oh, okay, so it's just like limited by the output of the map. Okay.
Yeah.
So
No, go ahead, but
does it matter if I choose like R5 or R6?
it matters if you want to visualize
Oh, yeah,
it, which
yeah.
makes it harder to
Okay.
visualize it with greater than R3, which is why it is in R3. In practice, no, it does not matter at
Okay.
all. So
And then another question I had.
Yep.
No, that part makes sense. Another question.
let me
I had-
just talk a little bit more about it, though, just so that it is clear across the board. I have an image that is in 3D1, D2. So the dimensions of the image, the backbone is this. It takes it, gives me an output that is like a flattened feature vector. This is, for example, in R of 3, and then I have a weight matrix that is just 3 times 1, so it gives me R of 1 output. So this is my classification, right? And this is the output of the penultimate layer. And this is this thing is what we are trying to visualize basically through that. Okay. So sorry, question? Yeah.
So my next question is like, how do you know the data is linearly, like, if you have more than, you have like, in this case, you have 3 means, right?
Yep.
If you have a linear SVM, are you trying to project it to a higher dimension, or?
The idea is that so this setup is not us using an SVM specifically. This is us basically building an analogy to an SVM. So SVMs are limited in the sense that you are only using them for our
Right, so you're doing like, you're trying to classify 3 classes here while you have a linear SVM, so.
No. So you don't have a linear SVM. I'm sorry. I'm saying that the linear SVM was an analogy. Here we are using a deep neural network. We're using the classification structure, but the behavior ends up being very similar to an SVM. So it is non-linear, of course, because it is able to classify image data, but the entire backbone is trying to just make the data linearly separable from being inherently not linearly separable. And then the final classifier is just doing the classification. So the hard work happens before that final linear classifier. It is basically the machine learning model input all the way up to here. Up until the last layer, yes, exactly. Right. Any more questions, brother? Questions are always good. Okay. If there are any more, just please interrupt me. That's always welcome. All right, sweet. So the idea behind this is that over the course of training, the variability of these points completely collapses, and it sort of tends towards these final points at the very end. And that is something that is incredibly valuable because that is the overall optimal structure, right? And it's something that we would not traditionally expect, because when we train when we train these models, we basically get to the point of the 100% accuracy and we kind of stop there, right? We don't try to go all the way up to, or like we don't try to force the training once we reach that point, but there is some value to actually doing that. And the very easy sort of alternative is that since we know that this setup is the optimal, we can kind of force it in the final state and not really worry too much about the setup. So the final layer just remains untrained and it tries to learn this structure instead of the final classification. And then you already have the optimal final layer that is present. Yes.
So after KI would be the logic for class K, like the logic in the vector. Penultimate layer.
The logic is the FKI times the weight. What weight in R theta.
Oh, because I thought every class would have its own element in the vector for like the penultimate layer. Like there would be a vector. The output of that layer would be a vector.
The output of FKI is the vector, correct?
Yeah. And it would show like for that specific class.
So the idea is that it kind of is doing that, right? It's basically giving each class its own basis.
Yeah.
Right. So it is placing class 1 on this page, class 2 on this page, class 3 on this page.
Yeah.
And that is something that is very cool. But by default, it is not doing that. It is just trying to make it linearly separable. If we have right now we are visualizing R3 for 3 classes.
Yeah.
What if you are doing that for 2 classes? Right, then it becomes a little bit more complicated because each of them won't have their own basis. So what instead it does is, and this is honestly a fantastic segue to it, it actually just tries to create what is a simplex ETF. Okay, also, I'm going to skip over all of the math. My target was to finish talking about DNC completely by 8:30 and 8:23. Just for context, because this is a recap technically. So I'm going to skip over all of the math, but the core idea behind the math here is that we are trying to find a way to empirically identify when we have reached a point of neural collapse. And since we cannot visualize it when we have arbitrary R, so if it's in R3, we can visualize it. If it's more, we can't. So the idea is to just create a numeric metric, a scalar metric that tells us how close we are from the state of neural collapse. There are 4 key metrics. So the first one is the collapse of variability, which we can compare using this setup. This one is actually important for later, but I guess we can come back to it if we need to. Aside is on pseudo inverses, which I will not talk about right now. The simplex ETF is the next part of the structure itself. So firstly, we identify the fact that the class means itself were reducing. So the variances of the data points to their class mean reduced significantly. Now we are going to talk about the actual structure itself. So if we have R of 2, so a penultimate feature vector outputting inputting R of 2, but we have 3 different classifications that we're trying to make. It becomes difficult to linearly separate those, at least much more linear, much more harder than if we have 3 in 3. So instead what it a better generalization of what it's trying to do, rather than saying it's trying to find or assign a basis to each class, is saying that it is just trying to create a simplex ETF, wherein we have a simplex ETF is really just a generalization of a triangle. So you have in 1 dimension, a simplex is a dot. In 2 dimensions, it is a triangle. In 3 dimensions, it is, sorry, in 2 dimensions, it's a line. In 3 dimensions, it's a triangle. In 4, it's a tetrahedron, and so on and so forth. The idea is basically that there are flat sides. And in principle, what we are really trying to do is just maximize the distance between each of those class means and maximize the angle between each of the class means. And this is kind of similar to Vesper theory in chemistry, where you have to increase the distance. Yeah, I know. Between the atoms and that is the basic setup of the molecule. So this kind of applies in a similar sense. That is the simplex ETF. Again, won't spend too long talking about that and how we set up the numeric metric, but the math is there. The other thing is that the final layer's weights align with the simplex ETF of M, which means that it is basically interpreting a simplex ETF. It recognizes the structure of the simplex ETF. And by the way, the weights over here this is what I'm talking about. So this is it effectively represents the structure of the simplex ETF, and this is in partially because the output itself is represents the form of a simplex ETF. And if at the end of your prediction sequence, right, where I get to this point over here, I want to start predicting the final class. The weight matrix basically just has to read a simplex ETF, right? Because it is compressing our inputs into this form of a simplex ETF. So it makes intuitive sense that this should happen. And there is again one more metric that can just show us the fact that it does hold. So we have this metric, and then the final one, which is possibly the simplest, it is us basically looking at the structure of our data and saying, hey, there is a simpler, more deterministic way of doing this than having this weight matrix over here to set up the final classification. And the answer to that is just KNN, where K is our number of classes. We basically just take the input point and compare that to the class mean, find whichever class mean is the closest, and say that is my classification now. And the ability to do that and the score that you get or the performance that you get if you use that approach to setting up your classification instead of this weight matrix is basically the NC4 metric. So we're basically just comparing how closely a KNN approximates the true result. And if each of the four metrics that we observed before are zero, then we can state that our model is collapsed. In the starting, it will not be the case. You will get values that are arbitrary and definitely non-zero. And it is something that we are not optimizing against. So when we reduce loss, we are directly training our model to minimize loss. In this case, we are not trying to do that. We are, it is just doing that kind of on its own as we overtrain our model. So we do want this. This was like a peculiar example where even with random labels, we are seeing neural collapse, and that is something that is interesting, surprising, but it is something that is pretty useful. This is the first thing is more a consequence of over parameterization of networks rather than the deep neural collapse itself. Although deep neural collapse does depend on over parameterization, they are similar but not the same. The other thing is that it also helps with out of distribution inference. If your data set or if your input is coming from a different data distribution, it is much likely, it is very likely that the outputs don't end up creating that simplex ETF. And it gives us a metric of saying, hey, potentially our data is not coming from the same distribution because it is no longer creating that structure. And possibly you should be unconfident about whatever prediction is made here. The other thing is that we can force the final layer to be an ETF instead of having it learn it over a long period of time. And the other thing is also the proven optimality of the deep neural collapse structure. Cool. So that was deep neural collapse. Are there any questions with respect to that? And if not, we can talk about AGOP. All right, cool. So average gradient outer product is a data-dependent backpropagation-free mechanism that characterizes feature learning in neural networks. Again, this is a mouthful, but luckily the math of it is actually relatively straightforward. We are given a data set X in RB0, could be anything, N of them. We have our input, or we have a function F, which is our neural network. And with these two things, we can define our AGOP. The important thing is that we are maintaining the notation from, I guess I didn't talk about the notation today. Okay. Or I guess I did talk about this part. We have K different classes. So capital K basically just represents each of the K classes and represents all the endpoints within the class. So if I have say 4 classes and I have 100 data points for each class, I have 400 classes. And the average gradient outer product is basically just the math is basically just spelling out the name, where I'm taking the average of my gradient. So gradient is the output of the neural network, and this is the output of the neural network in full, not only up to the parameter layer with respect to the input. And basically, we are taking the outer product of this gradient, and that gives us average gradient of the product. Why this is super important, we'll talk about now. But
Where you square, right? The dot product is, you know, like, times each.
this is not a dot product.
Um,
This is outer product. Inner product is dot product, right? It is, if I'm doing, let's actually.
My question is similar, like what is outer, I've heard the name outer product. I don't know
Oh,
what it is.
it's, okay,
I know what inner is.
inner, if I have this xtx, this is inner product. And outer product is just this xxt.
Aren't they the same? Because like, you're just like, they're like, so because inner product, right, you're saying that it's the summation of xi.
What if x, wait, if x is an R of 2/3, what will be the shape of the inner product? What will be the shape of the outer product?
Oh, I see. I was thinking that was the data. so I don't know.
Yeah.
I thought the output would be a vector. It would just be a vector with softmax values.
This is,
Or it's the one here.
this is the gradient with respect to the model. So we have the output of the model. This is f, what is it using? xci, right? And this over here is, wait, sorry. This over here is xci, right? So I am basically comparing or calculating this over here. This is what we are computing. Oh shoot, sorry. Is it frozen? It's frozen.
Would it really be matrix, or would it just be a time vector, the length of the parameter? If there's like 1,000 parameters, it would just be a 1,000 dimensional.
It is with respect to we have, this is the output of this model is an R of 1, and the gradient itself is in. Okay, this is what we are trying to compute. And we have xci, so the dimension of the vector slash matrix that we get is basically dependent on if you flatten this or not. So let's assume for simplicity's sake that we are flattening our input. So this becomes x. Can we, yeah, okay. X in R3 D1 D2. This is a vector, right? And this is a scalar. So our gradient should be in this dimension. It should be R3 D1 D2 vector.
The output product would be the same as the product. Right?
Uh,
So the input should be a vector, and the output should be a vector, and the gradient is also a vector.
I think not, right? Because we will have when we are comparing inner product and outer product, when you're taking transpose of a vector, you are basically considering a matrix in with one dimension. Yeah. So it will be the inner product is just going to be in R1, right? That is just the correlation of the, or like that's just the norm, right? That is just,
It would just be a Jacobian.
that's the square norm. What?
Would it look like a Jacobian, like
What?
the gradient?
This, I mean, this itself is the Jacobian, right?
Yeah, yeah, that's what it's asking.
Yeah, this is the Jacobian. It is by definition the Jacobian. You're right.
So it's
Absolutely
basically
correct.
Jacobian times transpose. Right?
Yes, correct. Exactly. Yeah, that's exactly what we're computing. Okay. More questions? Sweet. So, okay. Now, the other interesting thing that we can also infer from this setup is that we are obtaining at the end a symmetric matrix. The outer product itself is going to be in R of 3D1 D2 times 3D1 D2. This is going to be like AGOP, I guess. Right? So that is one interesting observation that will be relevant for SVT. Why is this useful is the other question. There is another metric or another mechanism called the expected gradient outer product. And I try to sort of understand from the paper what exactly they meant by this being the optimal. There was an interesting paragraph that I want to look at. Hang on a second. Yeah, it was this bit over here. Uh, AGOP of a learned predictor represents the expected gradient outer product or EGOP of the target function. Yuan has a paper on this. It is 36 pages, and I did not read it. So this is going to be me yapping for a second. But the one point that they mentioned is the low rank structure, which improves predictions. I don't know why it improves predictions, but empirically we've seen that techniques like LoRa have been used pretty successfully, and they rely on the fact that these large language models that generalize very, very well have a low intrinsic structure or a low rank structure intrinsically within their weights. So I'm inclined to believe that part. But it's by definition, expected graded outer product is just the expectation of AGOP over the entire distribution. And instead of using our parameter, our model that we have defined, we use some optimal model, F star. And with only a few examples or a small data set size, the average gradient outer product is able to approximate the expected gradient outer product very well. And that is an interesting property. So that was something that is really cool, but I don't know exactly or mechanistically why this holds true, but we can, I guess, kind of speculate. Any questions about this part? Yes.
Expected gradient height is the optimal model.
Absolutely, yes. It's the outer product of the optimal model over the entire data distribution. So we are computing AGOP over our data set,
Yeah.
right? And with our model, whatever model we have got at the end of the overtraining procedure, but there is still an optimal model at start that we are not guaranteed to have at the time. And there is a data distribution which we definitely don't have access to. So the expected gradient outer product is the metric that you would get if you had an optimal network and you had the entire data set distribution or the entire distribution. You evaluated
Possible value.
over all possible values, yeah, or over the entire distribution.
Or the true distribution.
Yeah, over the two distribution.
And you can approximate that with this almost anywhere, with almost any, on like not only like you take your name.
It has to be overtrained, but not optimal.
Oh, so as long as it's an overtrained model,
Mhm.
use that formula as well.
Yes.
You can get close to the actual expected, which is equal to like taking the that equation of overall data points. and dividing
Spot on. Yes, exactly. Yeah. Yeah. Awesome. And that's something that's super awesome, of course. What am I on time? Don't want to go over. Okay. Now let us talk about neural feature matrices, which is a little bit more deeper into the underlying structure of AGOP. So the neural feature matrices are the right singular vectors and values of each individual layer, and these fundamentally rotate, scale, not scale, reflect the input. They're basically performing transformations over our input data, and we will use singular vector decomposition to basically break down each of the transformations. So they are performing these transformations over specific directions and performing those uh, transformations with a specific magnitude. And NFMs basically allow us to decompose those transformations from one highly complicated transformation that looks very weird into a couple of more interpretable transformations, so we can understand what is intrinsically happening to the data. So this can be recovered by calculating the eigenvalues and the eigenvectors of W, T, W as well. So this is the inner product of the weight matrix. And this is something that is very important because it allows us to establish the backpropagation free nature of AGOP. So I mentioned earlier that AGOP is backpropagation free. I think I did at least, and that is very important because it means that it can be applied in settings that are much more general than just neural networks. And this is the formulation for that. I guess I can talk about that before. Yeah, each of the individual eigenvectors capture the relevant task directions, and the eigenvalues consequently represent the magnitude of the direction of the transformation. And these are basically used for identifying features, because if you are not really transforming your input, okay, if you're not transforming the input, nothing is really happening. That data is either consistent, or yeah, it is just considered consistent across layers. So the NFM is just that setup over there, and we can use SVD to decompose that. That would be again important a little bit later. Yeah,
What's W?
that's just a weight limit.
Oh, the weights of all of the models, right?
Of only a specific layer. Yeah, sorry. L is for layer.
Oh, yeah.
I made it subscript instead of superscript, which it was previously. And the
I represent.
each of the vectors and each of the vectors and the eigenvectors and eigen
In each layer.
for each layer.
Okay, so each layer would be like a matrix. The weights could be representing each layer of the matrix.
Yeah.
And then you can find the eigenvalues from
Yeah.
from the basis of the eigenspace.
Yeah.
Oh, I see.
Okay. See, these are defined for each intermediate layer. So for all of L from the input all the way to the final layer, and each NFM or neural feature matrices is correlates very deeply to the AGOP. So we defined AGOP earlier, and we can see that the correlation of the neural feature matrix is incredibly close to that of the average gradient artifact. And that is what makes it backpropagation free. And if we basically collect all of the NFMs or each of the NFMs across all of the layers, we will get a single entity, and that is called the neural feature ansatz. I still don't know if I'm pronouncing it right. But that is the set of weights, or like the set of matrices that define feature learning in neural networks. So there is like a very interesting property here. Bonus, it makes it backpropagation free. So I guess I did not mention it earlier.
So
Question?
is this in the correlation between the NFM that we know and the between our product is close to one?
Yes,
Okay.
exactly. That's
So it's something that follow almost a linear relationship.
Yeah.
So you can predict the value of them.
Exactly. So we are going to basically use the neural feature matrices as approximations of AGOP going forward because of this property. So we basically say that if I'm computing the AGOP for a particular layer, and I compute the LFM for the particular layer, they're sort of basically kind of approximating the same thing. And
If you have a linear relationship, what does that mean? You can't, like, you still go back to it. If you would say,
no, this is pretty sure exactly.
exactly the same.
Yeah, I may be wrong though. I'm not confident about what I just said. But yeah, I mean,
If you have a correlation of one, it just means that increase the equity.
let's check out paper. It's a good point. Okay, let me see if I can find it.
Respect something else.
Chris, or maybe I should. Give me 1 second. Let me find it. Oh yeah, here it is. Okay. It is correlation whose value is in -1, 1. And this paper formulates similarity as proportionality, which is equivalent to correlation. Okay.
You get like the corresponding value, it's basically scale it in that for all product.
Okay. I don't know enough. I'll take you on it. I think I'll trust you. So for all the layers, we are finding a correlation between the ground matrix of the input, or the cross correlation matrix of the input, with the AGOP, but I never I'm not 100% sure simply because I have not uh in none of the literature that I read, they mentioned the fact that there is a scaling factor involved.
Yeah.
So I could 100% be wrong and there is a scaling factor involved and it's just not relevant.
We get like from like the artist input that we can place and study, you just need to multiply by and constant. Multiply by constant.
I don't know that. I don't know that. I'm not confident that I'm not confident enough to say yes or no, is what I'm saying. From the literature I read, they did not mention a scaling constant anywhere. But that might not, that might be just too unnecessary for them to mention. And it may not be relevant to, or it may not affect any of the further discussion that we have. So it might not be a problem. But I will make sure to like check right after so we can know for sure exactly what exactly if there is a correlation factor or not. Okay, awesome. So that, any more questions? Okay, sweet. So question what exactly does the average gradient outer product find? It's a lot. We are at 50, so I'll not spend too much time on this. It is able to perform some interesting things because we're talking about image models. We can see edge detectors that are present over here. We can see that it is identifying curves and it is identifying things like a circular ball over here. It is identifying or performing some degree of edge detection here. And these are intermediate representations of the of AGOP that we have that are basically extracted from some of the intermediate layers. And as we go and progress to some of the later layers, features that are much more important or sorry, that are much more high level get constructed in the sense that we can see things like faces when we basically render the AGOP that we obtain for a particular input. So this is important to note that AGOP is data dependent, right? Because we are computing computing it with respect to our input itself. So that image to a certain extent is sort of reflected in the features because it is extracting those features to make the final direction, which is super cool. So we have that, and now let us talk about how the AGOP structure actually induces deep neural collapse. So one thing that I did not really talk about was something called deep RFMs or recursive feature machines, which is basically kernel regression that is applied recursively with AGOP as a mechanism for feature learning. So basically, we will use AGOP to extract features. So the right subspace or like the right singular subspace is basically extracted from the NFM, and that is sort of used as the mechanism for feature learning. And we basically combine the right singular structure of the NFM with kernel regression recursively in order to create a deep recursive feature machine. And that is sort of analogous to a neural network in the sense that it uses AGOP as a structure for learning, and it performs actually really well. So if you look at some of the images, I think we have the situation where we have the kernel plus AGOP. So we are using AGOP for feature learning, and that is improving the performance of the network. So that is something that is really interesting, which means that it is actively affecting the behavior of neural networks. Or not neural networks, but it has a potential of actively affecting the feature extraction in learning. And since we know that it is inherently present in neural networks, we identify the fact that deep neural collapse is actually caused by AGOP. So that is basically what this talks about. What? Okay, there was something that was supposed to be there in bold over there. Within variability, collapse occurs predominantly through multiplication by right singular structure of weights. Yeah, I don't recall what was supposed to be there over there. That's my bad. Okay, no. Anyways, so I'll make sure that the content itself that we're talking about is clear so that it's not a blocker. But the idea is that we will first take the waves that we have learned and for a specific layer and decompose it using singular vector decomposition. So we have the left singular vector u, the singular value matrix, and the right singular vectors or like the right singular matrix v. And that is basically the decomposition of the transformation that is happening by W sub L. So assume we have where is so if we look at what SVD fundamentally is doing, right? We have a matrix that is basically performing a transformation over an input, right? We have say R of if we have a matrix that is in R of n times m, it is taking in an input that is in, so we have W in R of m, and we have X in R of what is it? M, right? And if you do Wx, that is basically going to transform the data from R of m to R of n, right? And the idea is that it is performing a complex transformation with the constraint that the transformation has to be linear in nature. We can break down the linear transformation into a series of the scale, reflect, what is it thing? Rotate, scale, and reflect transformations or operations over the input, and singular vector decomposition basically does exactly that. Let me find. So I have some notes over here on SVD. So we have the rotation, which is carried out by the left singular. Oh, so we start with the right singular vectors because input goes from the right to the left in matrices. So we first perform a rotation operation over the data. Then we either add or erase dimensions. We this is by the singular value matrix. So if we have more the structure of the singular value matrix is just a diagonal matrix where we have values like x of 0, x of 1, x of 2, x of 3, and then everywhere else it is zeros. So if you want to add dimensions, all you have to do is just add 0 columns over here. If you want to erase them, you just kind of trim it, I think. And the idea is that the singular value matrix, does that, and then once that is done, it is rotated back into the output dimension, or no, we have the output dimension over here, and then it is rotated back to get our final output. So basically, what we are doing is we are kind of creating this line where we have this sort of section that is doing one kind of operation, and we have this section that is doing a different kind of operation. This is sort of an empirical distinction that is made where the authors of this paper are basically making the claim that the three things that are happening over here represent sort of one set of operations, and the rotate represents the other, where the first one is the operation of the feature extraction, which is AGOP, and then the left singular vector performs one type of rotation and the element-wise non-linearity that we are applying to the network. So going back to this, we first decompose our weight matrix using singular value decomposition, and we view the right singular structure as the input affine transformation, and then sigma and u as the element-wise, as applying element-wise non-linearity. One thing I don't follow myself here is why u sub L represents element-wise non-linearity, because it seems like it does seem like it is a linear transformation, but it could also be extracting valuable features for the next layer. But when they used the recursive feature machines to do the exact same thing, they omitted the left the left singular vector, and then they did not have any problem with the setup, and it was able to learn features just fine. So I guess I don't know, but speculatively it is not as important. So there is some mathematical derivation over here that is basically just us saying that computing the NC1 matrix over the right singular vectors is equivalent to performing it over W sub L. I'll skip the derivation for sake of time, but the key takeaway is that if you were trying to plot the collapse of or like, if you were to try to plot deep neural collapse uh, by splitting up the actual layer. So W sub L is just us dissecting the single layer into a bunch of separate transformations. And at the first stage, which is the right singular vector transformation, and then this is the entire this is the entire linear transformation, and this is the input, right? So the idea is that in each of these layers, we can see that the actual collapse happens after the green part, because if ReLU and U, the U matrix over here, were actually contributing to collapse, we would see the red line be significantly lower than the green line in each scenario, right? So basically, the idea here is that the collapse is being triggered by the operation that is in green, which is the input. So phi x is just the input, and then the right singular vector which is composed with the singular diagonal matrix, and we can see that the combination of that is basically what is inducing deep neural collapse.
And what is this connect to, AGOP?
So the neural NFM is the WL transpose W, which correlates with AGOP, and we are computing the NC1 matrix on the right singular vector decomposition of W sub L. So we basically are sort of approximating AGOP with NFM, approximating NFM with the right singular vector decomposition.
Oh, I see.
And they are close enough approximations that we can say that we are effectively identifying the fact that the mechanism of AGOP is the underlying thing that is inducing the collapse and motivating generalization in deep neural networks.
So can you show me the part on the screen where NFM is applied to the original configuration? So if I multiply to the right, by a right singular matrix,
Right.
you compose NFM,
Uh,
you trigger the flag,
yes, yes. So
where is that, where is that done?
we have a layer, like a layer of weight matrices, right?
Yeah.
And that is just the transformation from one dimension to the other dimension.
That's just the normal layer.
Normal layer part, exactly. So now we can represent that same weight matrix using singular vector decomposition as three matrices, right? And those three matrices are U, S, and V transpose.
Rotation, a translation, I think, and then another rotation.
Yes, exactly. The rotation, scale, and then another rotation. Right?
Yeah, but like, then you multiply by NFM to the right, is that what you do?
No, we don't, the NFM is intrinsically the SV transpose, that is NFM.
Okay.
So that the NFM exists intrinsically as part of the neural network.
I see.
Right? So basically the observation is that over here we're saying the fact that the neural feature matrix is what is actually creating or inducing the neural collapse. So generalization is improved because of the neural feature matrix part in the general architecture of the neural
So
network.
what causes it to start overfitting?
It's what causes it to start generalizing,
Okay.
right? So the variability collapse part and the NC1 and NC2 matrix basically NC1 and NC2 metrics basically depend on the deep neural architecture, right? And 3 and 4 don't really depend on that architecture. So their study is mainly focused on NC1 and NC2. And and in those cases, we are seeing that we know deep neural class occurs whenever all of the four metrics goes to zero.
Yeah.
And those two metrics basically go to zero because of the activity of the neural feature matrix. So when the neural feature matrix is applied to the input, that transformation reduces variance very significantly. So their interpretation is that a lot of the feature extraction, the real value of the neural network, right, is happening within those two matrices.
Essentially, it's observed that SV 5x approximates the NCM, right?
And SV transpose, not 5x, 5x is the input that comes into the model at the time.
Okay, so SV transpose approximates NFM, which approximates the average gradient.
Yes,
Um,
AGOP, yes.
Yeah, AGOP. And that basically, our product, and that basically tells us that since the green line goes down, at
Yeah.
the same time line collapses.
Yeah.
That since the
Well, the green line goes down implying the model collapse.
implied model collapses.
Yeah.
And since it correlates so heavily with AGOP.
Yeah.
When the AGOP has a lot to do with. Like,
Yes.
it's my model thing.
Exactly.
Okay.
Yeah. So they're basically saying that the feature extraction that is enabled is identified by AGOP, and that structure itself is what leads to generalization.
Okay, yeah.
Yeah, awesome. That was a very good summary of exactly what is happening. I think we are how much out of overtime? 3 minutes. So that's I think that's fine. I'm happy with that one. NC2, the structure of the simplex ETF was observed, but only in the last layer. That makes sense because we don't want we are creating the simplex only at the final layer because the structure of the classification exists only at the final layer. And that does not have to or like that does not that could be triggered. I think that is triggered by the NFM as well, but I do not see any plots that discuss that. So it just mentioned the fact that the NC2 structure was also observed for the final layer. That is all I have. If there are any more questions, I would love to take them, but if not, questions?
There were some implications. If we say that we can look at AGOP, and by looking at the average gradient on the product.
Yeah.
We can understand more about if the model is generalizing properly.
Yeah.
How can we interpret that in terms of like how we train the model and gather data?
So one strong way or one strong application of this approach is that we know that AGOP is the structure or the mechanism that triggers feature extraction in neural networks. So they developed the system of the deep RFMs that is basically kernel ingesting, but it just isolates the structure of feature extraction.
Okay.
So if I know the source of feature extraction and I know that some parts are not doing much, I will just use the parts that are actually doing stuff. And since since SVD breaks down the transformations into those stages that are understandable, we know exactly in what transformation is occurring in what direction using the SVD decomposition.
Oh, that makes a little more sense. So essentially, if we know to focus on the average gradient on the topic, if we look at that equation, we look at how it's being altered, like we're training.
We can observe it as a part of the training. We can create a new structure or new architecture that basically heavily relies on the AGOP for feature extraction. So it's basically like there is a gun, right? And then there is an attachment to the gun. It's not doing anything, but someone is using the entire gun. I just take out the attachment and I use the part that is actually shooting, and I will use that in a different setting, but the attachment is not required. So
Average gradient on the product is a function of the data set as well as the parameters, right?
right, yeah.
So you need to consider the data set when like looking at AGOP as well as the parameters. So given a data set.
You can do the data set as well as the parameters. Yeah, you're right, correct, absolutely.
It's a completely different data set. You have a different data, right?
Yeah, yeah.
Generation pattern completely changes.
Yes,
Yeah.
absolutely.
So basically, if you want to.
Well, so wait, sorry. One thing, if it is the same data distribution, but the same, like you're issuing data,
Like a completely different issue.
No, then, then you would have something completely different.
So if you want to, for example, prune your neural network to reduce the amount of parameters.
Yes.
You look at, given the data set that you know for sure will be training on.
One of the applications of AGOP is also reducing, network pruning, so
Okay,
that's,
so given D, you can look at the parameters, look at which parameters together with D contribute to the AGOP training. To help you better understand, which parameters are useful for predicting the features, and which ones can be removed from the.
yes, exactly.
Okay.
That's exactly how, that is one of the applications of AGOP, it is for future pruning, so that's,
Okay, thank you.
awesome. Thank you so much, have a great rest of your day, and we will see you all next week.
I think you can measure them. It's like in order to implement all of this, you first need to understand how
Wait,
how
what,
much more efficient.
was my video off the whole time?
No, I think the audio.
No, no,
The video was off.
video was off.
Yeah.
Oh, shit,
You're speaking.
oh, that sucks.